Configuring RAID logical volumes. You can create and manage redundant array of independent disks RAID volumes by using Logical Volume Manager (LVM). LVM supports RAID levels 0, 1, 4, 5, and 10. An LVM RAID volume has the following characteristics. LVM creates and manages RAID logical volumes that leverage the multiple devices MD kernel drivers. You can temporarily split RAID 1 images from the array and merge them back into the array later. LVM RAID volume supports snapshots. RAID logical volumes are not cluster aware, although you can create and activate RAID logical volumes exclusively on one machine. You cannot activate them simultaneously on more than one machine. When you create a RAID logical volume LVM creates a metadata subvolume that is one extent in size for every data or parity subvolume in the array. For example, creating a two-way RAID 1 array results in two metadata subvolumes LV underscore R meta underscore 0 and LV underscore R meta underscore 1 and two data subvolumes LV underscore R image underscore 0 and LV underscore R image underscore 1. Adding integrity to a RAID LV reduces or prevents soft corruption. RAID levels and linear support. The following are the supported configurations by RAID, including level 0, 1, 4, 5, 6, 10, and linear. Level 0. RAID level 0, often called striping, is a performance-oriented striped data mapping technique. This means that data being written to the array is broken down into stripes and written across the member disks of the array, following high input or output performance at low inherent cost but provides no redundancy. RAID level 0 implementations only stripe the data across the member devices up to the size of the smallest device in the array. This means that if you have multiple devices with slightly different sizes, each device gets treated as though it was the same size as the smallest drive. Therefore, the common storage capacity of a level 0 array is the total capacity of all disks. If the member disks have a different size, then the RAID 0 uses all the space of those disks using the available zones. Level 1 RAID level 1 or mirroring provides redundancy by writing identical data to each member disk of the array, leaving a mirrored copy on each disk. Mirroring remains popular due to its simplicity and high level of data availability. Level 1 operates with two or more disks and provides very good data reliability and improves performance for read-intensive applications but at relatively high cost. RAID level 1 is costly because you write the same information to all of the disks in the array, which provides data reliability but in a much less space efficient manner than parity based RAID levels such as level 5. However, this space inefficiency comes with a performance benefit which is parity based RAID levels that consume considerably more CPU power in order to generate the parity, while RAID level 1 simply writes the same data more than once to the multiple RAID members with very little CPU overhead. As such, RAID level 1 can outperform the parity-based RAID levels on machines where software RAID is employed and CPU resources on the machine are consistently taxed with operations other than RAID activities. The storage capacity of the level 1 array is equal to the capacity of the smallest mirrored hard disk in a hardware RAID or the smallest mirrored partition in a software RAID. Level 1 redundancy is the highest possible among all RAID types, with the array being able to operate with only a single disk. Present RAID level 4. Level 4 uses parity concentrated on a single disk drive to protect data. Parity information is calculated based on the content of the rest of the member disks in the array. This information can then be used to reconstruct data when one disk in the array fails. The reconstructed data can then be used to satisfy input or output requests to the failed disk before it is replaced and to repopulate the failed disk after it has been replaced. Since a dedicated parity disk represents an inherent bottleneck on all write transactions to the RAID array, level 4 is seldom used without accompanying technology such as write back caching, or it is used in specific circumstances where the system administrator is intentionally designing the software aid device with this bottleneck in mind, such as an array that has little to no write transactions once the array is populated with data. RAID level 4 is so rarely used that it is not available as an option in Anaconda. However, it could be created manually by the user if needed. The storage capacity of RAID level 4 is equal to the capacity of the smallest member partition multiplied by the number of partitions minus 1. The performance of a RAID level 4 array is always asymmetrical, which means reads outperform writes. This is because write operations consume extra CPU resources and main memory bandwidth when generating parity, and then also consume extra bus bandwidth when writing the actual data. It is because you are not only writing the data but also the parity. The read operations need only read the data and not the parity unless the array is in a degraded state. As a result, read operations generate less traffic to the drives and across the buses of the computer for the same amount of data transfer under normal operating conditions. RAID level 5. This is the most common type of RAID by distributing parity across all the member disk drives of an array. RAID level 5 eliminates the write bottleneck inherent in level 4. The only performance bottleneck is the parity calculation process itself. Modern CPUs can calculate parity very fast, however, if you have a large number of disks in a RAID 5 array, such that the combined aggregate data transfer speed across all devices is high enough, parity calculation can be a bottleneck. Level 5 has asymmetrical performance and reads substantially outperforming writes. The storage capacity of RAID level 5 is calculated the same way as with level 4. RAID level 6. This is a common level of RAID when data redundancy and preservation and not performance are the paramount concerns, but where the space inefficiency of level 1 is not acceptable. Level 6 uses a complex parity scheme to be able to recover from the loss of any two drives in the array. This complex parity scheme creates a significantly higher CPU burden on software RAID devices and also imposes an increased burden during RAID transactions. As such, level 6 is considerably more asymmetrical in performance than levels 4 and 5. The total capacity of the RAID 6 array is calculated similarly to RAID level 5 and 4, except that you must subtract two devices instead of one from the device count for the extra parity storage space. RAID level 10. This RAID level attempts to combine the performance advantages of level 0 with the redundancy of level 1. It also reduces some of the space wasted in level 1 arrays with more than two devices. With level 10, it is possible, for example, to create a 3-drive array configured to store only two copies of each piece of data, which then allows the overall array size to be 1.5 times the size of the smallest devices instead of only equal to the smallest device. Similar to a 3-device level 1 array, this avoids CPU process usage to calculate parity similar to RAID level 6, but it is less space efficient. The creation of RAID level 10 is not supported during installation. It is possible to create one manually after installation. Linear RAID. Linear RAID is a grouping of drives to create a larger virtual drive. In linear RAID, the chunks are allocated sequentially from one member drive going to the next drive only when the first is completely filled. This grouping provides no performance benefit as it is unlikely that any input or output operations split between member drives. Linear RAID also offers no redundancy and decreases reliability. If any one member drive fails, the entire array cannot be used and data can be lost. The capacity is the total of all member disks. LVM RAID segment types. To create a RAID logical volume, you can specify RAID type by using the -type argument of the LV create command. For most users, specifying one of the 5 available primary types, which are RAID 1, RAID 4, RAID 5, RAID 6, and RAID 10, should be sufficient. The following table describes the possible rate segment types, LVM rate segment types, segment type description, rate 1 mirroring. This is the default value for the hyphen type argument of the LV create command. When you specify the hyphen argument without specifying striping, rate 4 dedicated parity disk, rate 5 underscore LA, rate 5 left asymmetric, rotating parity 0 with data continuation, rate 5 underscore RA, rate 5 right asymmetric, rotating parity and with data continuation, rate 5 underscore LS, rate 5 left symmetric, it is same as rate 5, rotating parity 0 with data restart, rate 5 underscore RS, rate 5 say right symmetric, rotating parity and with data restart, rate 6 underscore ZR, rate 6 0 star restart, it is same as rate 6, rotating parity 0 left to right with data restart, rate 6 underscore NR, rate 6 N restart, rotating parity and left to right with data restart, rate 6 underscore NC, rate 6 N continue, rotating parity and left to right with data continuation, rate 10 striped mirrors. This is the default value for the hyphen type argument of the LV create command. If you specify the hyphen M argument along with the number of stripes that is greater than 1. Striping of mirror sets rate 0 or rate at 0 underscore meta. Striping rate 0 spreads logical volume data across multiple data subvolumes to units of stripe size. This is used to increase performance. Logical volume data is lost if any of the data subvolumes fail. Parameters for creating a rate 0. You can create a rate 0 striped logical volume using the LV create hyphen type rate 0 in square bracket meta in angular brackets meta hyphen stripes underscore stripes hyphen stripe size volume group physical volume path command. The following table describes different parameters which you can use while creating a rate 0 striped logical volume. Parameters for creating a rate 0 striped logical volume parameter description hyphen type rate 0 underscore meta specifying rate 0 creates a rate 0 volume without metadata volumes. Specifying rate 0 underscore meta creates a rate 0 volume with metadata volumes. Since rate 0 is non-resilient, it does not store any mirror data blocks as rate 1 or 10 or calculate and store any parity blocks as rate 4, 5 or 6 do. Hence, it does not need metadata volumes to keep state about resynchronization progress of mirrored or parity blocks. Metadata volumes becomes mandatory on a conversion from RAID 0 to RAID 4, 5, 6 or 10. Specifying RAID 0 underscore meta pre-allocates those metadata volumes to prevent a respective allocation failure. Hyphen stripe space type specifies the number of devices to spread the logical volume across. Hyphen stripe space stripe size specifies the size of each stripe in kilobytes. This is the amount of data that is written to one device before moving to the next device. Volume group specifies the volume group to use. Physical volume path specifies the devices to use. This is not specified. If this is not specified, LVM will choose the number of devices specified by the stripes option, one for each stripe. Creating RAID logical volumes. You can create RAID 1 arrays with multiple numbers of copies according to the value you specify for the hyphen M argument. Similarly, you can specify the number of stripes for a RAID 0, 4, 5, 6 and 10 logical volume with the hyphen I argument. You can also specify the stripe size with the hyphen L argument. The following procedure describes the different ways to create different types of RAID logical volume.